Hi, I'm Neil, and I'm joined by my team, Ruchi, Ryan, Calista, and Andrew, to present our project, a random forest analysis of remote sensing-driven mosquito habitat prediction in West Africa. Mosquito vector-borne diseases such as dengue, West Nile virus, malaria, and more pose a significant global health risk to millions of people. Therefore, there is a need for intelligent and automated mosquito habitat prediction models to assess mosquito abundance. These forecasting models would enable healthcare and government authorities to better address areas of interest that may be at risk for mosquito vector-borne illnesses. Our work aims to answer this research question: how effective are random forest models at predicting mosquito habitats in Benin using remote sensing environmental data? Additionally, our research offers a novel approach to mosquito prediction by performing a time series analysis on exclusive remotely sensed globe data in a unique location, Benin, via multiple factors to accurately predict mosquito abundance.
By plotting the Globe Observer app's mosquito habitat mapper data in ArcGIS, we were drawn to Africa and found that the country Benin had a significant amount of data. The larger amount of globe data available in Benin demonstrates the impact of mosquito population on the community, contributing to our desire to study this area. Furthermore, Benin has relatively stable climate patterns and publicly accessible data we can use to predict mosquito habitat abundance. Historically, Africa has faced constant mosquito outbreaks, and our project would be impactful for forecasting future outbreaks and developing prevention strategies.
To approach our research question, we started with globe mosquito habitat mapper data and 4 remote sensing environmental data sources at our target location. We isolated the years 2018 to 2022 and concatenated all the datasets. We filled null larvae count values with zeros and accounted for the imbalance of zeros through oversampling. We trained both a random forest regressor and a random forest classifier to predict mosquito larvae counts as numerical values or levels of abundance, and we hyperparameter tuned our model through random search optimization. Finally, we used evaluation metrics to evaluate the accuracy of our prediction models.
For our climate data, we use NDVI, humidity, rainfall, and temperature data. In order to merge all these datasets into one, we used the Globe MHM dataset as the base and matched appropriate measurements with the correct date and location. The rainfall and NDVI datasets we were merging had hundreds of observations on the same day, so we decided to average the values in order to accurately represent the day. Once all the datasets had one value per day or location, we began to assign them to the corresponding observation in the Globe MHM dataset.
After creating a combined dataset in order to train our model, we had to eliminate unnecessary data as well as account for data imbalance, which leads us into preprocessing. We first used the larvae count column to create a new column to classify larvae into 3 tiers. Then we dropped the data and location variables so our dataset only included our 4 environmental features and our 1 classifying feature. We split our data into a 90-10 train split, and since our data had an influx of zeros, we ensured a consistent test by using random state.
Here's what we found from training our model. The random forest classifier achieved its best accuracy at 85.12%, and looking at our confusion matrix, we can see that the data was overtrained with zeros and simply did not have enough data with the label of magnitude 1 or 2 to make the accurate decision. That's why our model favored predicting zeros, where rare instances which would actually guess a 1 and almost never guess the magnitude of 2. Random forest classifiers proved to be well suited for predicting mosquito habitats in Benin. While predicting the true mosquito larvae count also has its benefits, categorizing the larvae count into a tier system like ours holds real-world relevance to aid healthcare and government authorities in understanding the threat of mosquitoes in their area and making plans to address the future disease prevention. This study was limited by the availability and accuracy of the data we acquired, since Globe Observer mosquito habitat mapper observations come from citizen scientists. It may be important to acknowledge the lack of accuracy or consistency in data collection between observations. For example, the use of manual versus automatic location mapping, or the types of tools available to volunteers, such as microscope lenses, may affect the accuracy of the observations and thus may be important features to consider in our classification model. In addition, due to the inconsistent nature of our data, the number of representative data points to use in our dataset was also very limited. And our model could definitely be improved by acquiring data with regular and consistent mosquito observations.
In conclusion, our project demonstrates the implementation of random forest machine learning models to predict mosquito larvae abundance in Benin. Our results provide valuable insights for future research to apply machine learning architectures to remote sensing data in other target areas, and to develop surveillance or alert systems to aid in mosquito-borne disease prevention efforts. Based on these results, future work could leverage additional features such as location and date, or integrate more mosquito datasets from other sources, such as iNaturalist or Mosquito Alert, to acquire more consistent data for improved prediction accuracy.
Many thanks to the NASA and peer mentors for their insight and support, and thank you to all the SEAS coordinators who worked to organize this program. We thank the audience for listening, and we are open to any questions you may have.